Um, okay, so we left off talking about magnets in relation to compasses, and talking about Stranger Things, and how they were using their compasses to find the upside down, right? The gate to the upside down. Well, it's all those compass stuff has to do with Earth's magnetic field, right? The planets. I don't like the red. I'm going to switch to green. Here we go. The planet's magnetic field exists within the Earth, extends many hundreds of miles into space, right? Aurora Borealis, the northern lights, Aurora Australis, the southern. I didn't even know that. I didn't know that the southern lights are called Aurora Australis. That makes sense because Australia is in the south, southern hemisphere, are associated with the magnetic field. And then, although the field is weak compared to magnets used in the laboratory, it is thought that it is thought that certain animals can use it for navigation, and that's what you hear about the birds flying south for the winter to keep warm and such, right? Um, so uh, there was something super interesting I wanted to say about Earth's magnetic field. Oh yeah, so you know how the sun is beating down on us with all of its rays, right? And we already know that, if you're out in the sun for too much, you get sunburned, and then so the UV light passes through, and you get sunburned, and you might get skin cancer. But also, though, the sun also, like, every once in a while, will unleash these things called solar flares, and they're like huge things of fire, like hot, uh, solar flares that come from the sun. And the reason why they don't hit Earth is also because of the magnetic field around Earth. It also protects the the magnetic field around Earth. Not only protects us from that, it also protects us from the crazy gamma rays and X rays from the sun, because the sun actually produces all kinds of um, electromagnetic radiation, right? And so Earth's magnetic field somehow protects us from all that stuff, and you'll see why in a second. So here's a picture of Earth, and here's Earth's magnetic field, similar to the pattern from a giant bar magnet present within the Earth. Not, but there isn't one present though. So this is the interesting thing about it, right? Um, the North Pole is up here, right, and the South Pole is down here. But when you're using a magnet, the South Pole of the magnet is pointing towards the North Pole of the Earth, right? So I think a lot of people, including myself, when they're using a compass, they think that the North Pole, the north part of that magnet, is pointing to the north of the North Pole. But it's actually the south part of the magnet that's pointing to the north, right? So it's actually kind of opposite, right? And so that's really interesting. But the other thing that's interesting about it too is that uh, there's a difference between geographic North Pole and actual magnetic North Pole, right? So the North Pole that we think of, where Santa Claus is and all that, right, is right here, geographic North Pole. But magnetic North Pole is actually kind of over here, right? And depending on where you are, it can actually turn. It can actually like flare up and down like this, right? Where the magnetic North Pole, depending on where you are standing on the Earth. Same thing is true of the South Pole. The geographic South Pole, where Antarctica is right here, right? But magnetic South Pole is actually all the way over here. So if you're using a compass going towards, say, the North Pole, right? And depending where you are, say you're in like, say, it's hard to tell. Okay, so you're in Texas, say, right? Say you're in Texas right here, and you're using a magnet or a compass to go to the North Pole. You're going to end up over here in like British Columbia, Canada, right? Not actually at the North Pole. So it really depends on where you're standing to make sure that you're going the right direction to get to the North Pole if you're trying to find Santa Claus. I mean, it is the holidays after all. So I think most people use compasses to go places that are much more near anyway, not as far as the North Pole, so it's not that big of a deal. But it's just an interesting thing that magnetic North Pole is actually different from geographic North Pole. I always thought it was the same thing, right? So some interesting things about Earth's magnetic field, right? It turns out that we have no idea where Earth's magnetic field comes from. Like scientists don't know why the Earth has a magnetic field, right? They think that maybe it's probably related to the internal currents of electrically charged particles in the liquid outer core of the Earth in association with the Earth's rotation, right? But if you remember last week, or not last week, last Monday, I was talking about how if you reach a material's Curie temperature, right, and someone put like absolute zero or something for that question, right? Anyway, if you reach a material's Curie temperature, it no longer is magnetic. It cannot be magnetic anymore, right? And if you didn't know this, just below the Earth's crust is called the mantle, right? And just below the mantle in the center is called the core, and it's all molten, right? All molten magma, right? It's not lava until it comes out of the Earth's crust, but while it's still under the Earth's crust, it's called molten. It's called magma, and that shit's hot. Okay, it is really hot. Okay, and so uh, we're definitely exceeding the Curie temperature of most materials when we get as hot as it is in the magma, right? But somehow, even though we are above the Curie temperature of what we would consider magnetic materials like iron, cobalt, or nickel, right? The poles somehow still have a magnetic currents. The Earth still has magnetic currents, and we don't know why. Isn't that crazy? You think we would know something that simple, why the Earth has magnetic currents, but we don't know why. It's a little crazy. It's just a little bit crazy. And the positions of the magnetic poles are constantly changing, which suggests currents. That's what I was just talking about a second ago. You could be in Texas trying to get to the North Pole, but you end up in British Columbia or something, right? Instead of going to the actual North Pole. Uh, Crazy stuff right there. So here's your first question for today. Which of the following is not true about Earth's magnetic field? It's not well understood. It is ferromagnetic, or magnetic poles are constantly changing, or all these are true. Where the heck is that one at? Show more generators. Earth's magnetic field. There it is. Got 15 responses so far. Ooh, look at that. I'm actually very impressed that some of you got this one right. It was a little tricky. It's a little tricky. Very impressed. Very impressed. I'm very impressed because this was actually sort of a difficult, not a difficult, but tricky question, right? We know that things that are magnetic are usually ferromagnetic, right? But since we have a Curie temperature that has been completely exceeded in the Earth's mantle, it can't be ferromagnetic, right? So the answer here is that what is not true about Earth's magnetic field? It is ferromagnetic because it's not ferromagnetic. We don't know what it is that makes the Earth's magnetic field magnetic, right? It's crazy stuff, man. Crazy stuff. Yeah. That hand was like attached to that gun like a magnet to the Earth. So it's not always like it is in CSI where you're at like some rich person's house and there's a little blood there, and everything's beautiful. It's mostly you're getting dirty every day at 2 o'clock in the morning, So let me just tell you, bad crimes never happen during the day either. It always happens at night, or they get found at night, right? Oh man, funny thing about that, I got that gun working too, man. It wasn't working, and I fixed it, and so I was able to shoot test fires and match that gun back to the bullets that were in the cop and in the victim. It was amazing. That was even though the suspect was dead, but we had to make sure that was the guy that did it. And I was very proud of that case. Anyway, magnetic declination, right? This is the angle between the geographic true north and magnetic north, right? So what that is this right here, this angle, right, where you have magnetic north, right, and then the true north, right. So here's true north. This is this right here, right, and then there's an angle, and this angle between the magnetic north and the true north is what we call the declination angle, right. So the magnetic declination varies upon where you are on Earth. This is what I just said a second ago. And so in the northern hemisphere, the magnetic North Pole is about 1,500 kilometers from the geographic North Pole, right? Wow, I didn't know that. That far away? Wow. Therefore, a compass does not point you to true north, but to rather magnetic north, right? So an adjustment needs to be made called the magnetic declination must be made to determine the true north from a compass. So here I am in Texas, right? Here I am in Texas, and there's the North Pole right there. Well, I guess if you're in Texas, you'll get to the North Pole viewpoint, but if you're over here, maybe in Florida, you might end up over here, and I think that's British Columbia. I mean, I don't know. I'm not Canadian, so who knows, all right? Oh, I should have said Alaska because Alaska's way up there. Yeah, exactly. That works. Anyway, so so here we are in the United States, and these are the magnetic, uh, uh, not magnetic. What are they called? What are they called? Longitude lines, right? And these are the longitude lines, right? And here's the North Pole right here, right? And what happens then is that you have to put a compass, like I was saying before, right? You have to put a compass. If you remember this, so this is the compass right here, north, south, and east, right? And here's the compass needle. And if you want the compass needle, right, to point actually at the North Pole, you've got to turn the compass, right? You've got to turn the compass dial so that the needle is pointing towards magnetic north, and magnetic north actually lines up with the North Pole. And so the amount that you turn it, that dial that you turn it, is this dial right here. That's a little sigma, and this part right here is called the magnetic declination. Okay, good stuff. Good stuff. So notice here, it depends on where you are, right? But the angle is always different. For example, here we are. Here we are. Oh, these aren't longitude lines. These are actually magnetic lines. I apologize. And here we are. You're 20 degrees. You have to turn it. Wow, 20 degrees is a lot, right? That's a lot. That take you somewhere else. 15 degrees is the angle here. 10 degrees. So I guess if you're in like, oh, in Alabama, my home state. If you're in Alabama, you don't have to turn your compass at all. That explains that, right? That explains why the people in Alabama don't really know how to use compasses, right? They just they just use it as is. But maybe it's because they know how to use compasses and they knew that they didn't have to, change the angle at all, right? But anywhere else in the country, you'd have to change the angle that many degrees to get yourself to actually the North Pole, right? Kind of cool, kind of cool. So that brings us to electromagnetism. Okay, electromagnetism. Electromagnetism is the interaction of electrical and magnetic effects, right? There are two basic principles here. There's moving electric charges or a current, right? Because what is electricity? Electricity is just the movement of electrons, right? So moving electric current, I just changed the batteries. What the heck? There we go. Moving electric current, right, or charge gives rise to a magnetic field. That's the basis for the electromagnet, which I talked about last time, right? When you wrap a wire around a nail and attach it to the battery, and it makes a magnet. You can pick up things like paper clips with it, like they do on Bill Nye the Science Guy, right? So that's the basis for that. And then a magnetic field will deflect a moving electric charge. And that's the basis for motors and generators, right? So interestingly enough, this here, right here, shows the electromagnetic waves, right? And so the green here is the magnetic field, and then the electric field is the blue wave. And if you look at it, right, the blue, which is the electric field, is going up and down, right? Up and down. Whereas the magnetic field, the green, is actually going side to side, right? So if I ask you a question about this, right, just know that the electric field is going in the y direction, up and down in the y direction of a graph, right? And then the magnetic field is going perpendicular to that, right, on the x direction of the graph. Does that make sense? It makes this, if you look at it head on, it looks like a cross, right? Yes. And then this here is just the propagation of the direction of propagation right there, right? That's the direction it's going, direction it's moving. Right. So magnetic force on moving electric charge. When a moving charge, a current, again, enters a magnetic field, the moving charge will be deflected by the magnetic field, right? And we call this the magnetic force, right? The magnetic, so that's F mag, right? Which is the magnetic, that's kind of a cool name, F mag. I mean, that's like a gun or something. Anyway, we have F mag here, and it's perpendicular to the plane formed by the velocity vector moving in the charge in the magnetic field. which is the same thing I just told you about, oops, which is the same thing I just told you about this, right? It's perpendicular right here, right? The magnetic field is perpendicular, right? So again, the magnetic force is perpendicular to the plane formed by the velocity vector of the moving charge and the B magnetic field. So the things I need you to know from this slide here is that F mag is magnetic force, velocity vector is V, vector has always been V, right? And then magnetic field is B. Do not confuse the magnetic force and the magnetic field, okay? The magnetic force comes from the magnetic field, right? But they are not the same thing, okay? They are not the same thing, okay? Remember, F mag, magnetic force, V for velocity, B for magnetic field. Oh my gosh, look at this question here. Which of the following is a symbol for magnetic field? I'm just going to shoot for 90% of you getting this right. Well, you know what? Maybe 98%. Since really there's only one rebel, so we'll do 98%. I'm shooting for 98% of you getting this one right. There it is, mag field. Oh, 20% of 20 of you guys are in already, right? Oh my God, that's crazy. Oh, you know what happened here? You guys are smart because I screwed this one up. Okay, because that was supposed to be a capital B. That I'm sorry about that. Good call, guys. Good call. I was like, man, these people are idiots. But then I realized I was the idiot. So, so yes, the vast majority of you got that one right. The answer would be none of the above. If I had gotten that right there, that was supposed to be a capital B, right? So good job there. Good job. Good job there, right? Yeah. So maybe I should check myself before I start judging you guys, right? So, well, yes, you are correct. Little b is definitely not. Little b is definitely not magnetic field. Big B is magnetic field. Okay. All right. So let's talk about magnetic deflection, okay? Magnetic deflection. And so these are the type of pictures I might show you, right, during an exam, okay? These are the type of pictures I might show you during an exam. Um, Electrons enter a magnetic field experience a force, right? And it deflects them out of the page, right? So here is the electron, okay? Or for example, electric current or something, but electron, right? And you have a magnetic field here, big B, between the north and south pole, okay? And when this electron enters the magnetic field, it doesn't go straight through the magnetic field, right? It actually comes out of the page towards you, okay? Does that make sense? Right? This picture here showing this here, it's actually coming out of the page towards you. So you have to think about this in 3 dimensions, okay? You're coming from the left, you're wanting to move to the right as an electron, but since you enter the magnetic field, instead of going from the left to the right, you go from the left to out of the board. Make sense? Okay. Okay. And we can use that to actually do work. So check this. Check this wizardry out. Right. This wizardry. Right. Magnetic force on a moving charge. Right. A beam of electrons can be deflected downward due to the introduction of a magnetic bar. Magnetic field of a bar magnet. So here we have some electrons flowing, right, inside this little tube here, right, this little tube. And when you have it so that, I think that says the north side. Is that the north side? Yeah, I think that's the north side. When you have it on the north side of the magnet, right, and you bring it towards the electron flow, right, it actually pulls the electrons toward it. And then if you have it on the south side, I think I have it backwards. I can't tell what that says. Oh, that's south. I did have it backwards. So you have it on the south side, right? You have it on the south side, and it pulls the electron flow towards it. And then over here, you have it on the north side, and it actually repels the magnet. Repels the electron. So that's pretty neat. That's a cool um, little science experiment you can show kids. You know, make sure they don't touch the metal or anything like that because you might get electrocuted. But other than that, it's kind of cool to show, right? So since a magnetic field deflects a moving charge, a current carrying wire loop will experience a force, and that force you saw was the force of the electrons moving up and down. Okay, good stuff. Good stuff. So a stationary wire a stationary wire with no current will not experience a force in the magnetic field. So here we just have a wire, right? And if you just put that wire between a magnetic field, nothing is happening, right? That's just like a copper wire, okay? That's just like a copper wire. But then, say you put a copper wire, right? Say you put that same copper wire between the two magnets, right? And then you electrify it, then you have a magnetic force pushing out of the wall again, or out of the board towards you, right? This is towards you, and it's coming out of the wall again. Okay, it's coming out of the wall. So it's the same thing as we saw in that the previous two slides where we saw the electrons flying out like that, right? But here the electrons are actually still inside the wire, but the magnetic force that it shows comes perpendicular out of the page or out of the wall, just like on the free flowing electrons. Okay. So your next question is this: a current carrying wire in a magnetic field experiences a force in what direction? Parallel with the flow of the current? In the direction of the magnetic field? Perpendicular to both the magnetic field and the flow of current? Or none of the above? None of the above. All right, let's see how people are answering this question. What direction? Wow. Wow, wow, wow. Okay, I got 11 answers so far, still waiting. So only 13 answers, right? We need like 22 here. All right, we're at 18. We're at 20, 21. That's good because I think someone's missing. All right. Good job. The vast majority of you got that one correct. The answer is C, right? C, perpendicular to the magnetic field and the flow of current, right? Perpendicular out towards you, okay? Out towards you. All right, all right. So that takes us to talking about motors, because it turns out when you have a magnetic field and a flow of current, you can make work. You can do work with motors, right? So an electric motor is a device that converts electrical energy into mechanical work, right? When a coil or a coil wire, whatever. When a loop of coil is carrying a current within a magnetic field, the coil experiences a torque and rotates, right? That's cool. That's neato mosquito, as I always say. So let's see that in action, okay? So here we have a DC motor, a direct current motor, right? And see, we have a magnet here. We have a north side magnet and a south side magnet, right? And what happens is that you can flow electricity through this split ring commuter right here, right? And I'm pretty sure that means battery, right? Is that battery? Who knows? Everybody know? Somebody in here told me that battery was this symbol, I think. I'm pretty sure it's battery. Just take my word for it. That's battery. Okay? So if that's the electrical power source, like a battery, right? And you're flowing the electric current through this little thing here, this little split ring loop, commuter loop, right? And the electric current is flowing through this big wire loop here, right? What's interesting about it is that since the flow of since the magnetic field is this way, right? And then the electricity is going this way, right? It forces the loop to go up, right? On the north side, and on the south side, it forces the loop to go down. And if you keep that going, it spins, right? If you keep that going, it spins, right? And so what you can do now is you can have something over here that you need to turn, right? To do work. For example, your um, KitchenAid stand mixer, right? Or your engine, your car engine or something, right? You need to turn it, and that's how you can turn it. It's pretty cool, right? And so this picture here, right, just shows how if you have the coil like up and down like that, right, it's unstable because the magnetic force is pushing down on itself. So it doesn't want to stay that way, right? It doesn't want to stay up and down, right? It wants to start turning. And so when it turns, it forces it to turn because it's unstable, right? And it turns in this direction again, right? And then all this is in that magnetic field that we see up there, right? And this can just keep on going. It's pretty cool as you keep on pulling electricity through it anyway. So a split ring commuter reverses the loop current every half cycle, enabling the loop to rotate continuously, like I was just saying. The inertia of the spinning loop carries it through the positions where the unstable conditions exist, right? It doesn't want to be in the unstable conditions. So it's just going to keep on rotating to keep it out of its unstable positions. Okay, that's pretty neat. A good old DC motor, right? So what's a good example of a DC motor? Oh, like drones use that. Drones, like aerial drones use that. Um, remote control cars use that. What else uses that? Did you guys ever, as a kid, have those plastic Power Wheel cars that you drove around? Like I used to have a Jeep that I crashed, just like I crashed my go kart into the garage door. I'm a terrible. I mean, I'm Asian. Come on, a terrible driver. So, um, I mean, even at that age, I was a terrible driver. So, but yeah, all those cars and all those vehicles that you drive or you move around that they only run on battery, right? Those are all DC motors. They all work like this. It's kind of cool. Okay, so motion and induced current. The basic principle of an electric generator. Okay, this is how we generate electricity, for example, right? When a wire, I swear, what the heck? What the heck? I guess green lasers just really take up a lot of energy because the batteries don't last very well in a green laser. Either or I'm just talking too much. All right, so when a wire is moved through perpendicular to a magnetic field, the magnetic force causes the electrons in the wire to move. Therefore, the current is set up. Therefore, a current is set up in the wire, right? So you move a wire into the magnetic field, right? And so that's the V there, where you're moving. Like, say you had two magnets just pointing at each other like this, and then you put a wire through it. You run a wire through it, and the magnetism, the magnetic field, actually makes the electrons inside the wire move. And so that is an electric current, and you can get electricity from that. So that's the basis of making an electric generator, right? So a generator is a device that converts mechanical energy to electrical energy, right? So the mechanical energy part is the movement of the wire into the magnetic field, right? And when you move the wire into the magnetic field, you make the electrons in the wire move, and that's now called electricity, right? Generators operate on the principle of electromagnetic induction. Man, it's really hard to see the red laser, isn't it? Terrible. Anyway, do I have a yardstick? I could use this pipette. I just have to be really careful because it's glass, right? Okay, so generators operate on the principle of electromagnetic induction, right? And so electromagnetic induction was actually discovered by a guy named Michael Faraday in 1831, right? 1831. You may have heard of Faraday before. He's the proprietor of the thing that we call the Faraday cage, right? And that's not some kind of like, uh, BSDM kind of thing. It's not like one of those things. No, the Faraday cage is the thing that you can sit inside, right? And it blocks out all cellular signals, right? It blocks out all cellular signals. Okay. So nothing electronic will work in that. Well, sorry, let me rephrase. Electronics will work inside it, but if you have to get a signal from the outside, it blocks all signals from the outside, right? So your Wi-Fi won't work in there, your cell phone won't work in there. You can still play games because you don't need any kind of like, well, maybe if you need, do you need Wi-Fi or internet or signal to do Candy Crush? I don't know. Anyway, but yeah, that's what a Faraday cage is. So if you want to just unplug from the whole world, go inside of a Faraday cage. A lot of people say that this building is a Faraday cage because they can't get a good cell phone signal in here, right? Which makes kind of sense because this building was made like in the 50s, right? And so there's like steel bars all throughout all the walls, right? And all those steel bars make it very difficult for like cellular signal to get inside the building. It's even hard for your Wi-Fi signals to work in here, even though the Wi-Fi antennas are inside the building, right? So that guy, his name was Faraday. He came up with that, right? Or he discovered that anyway. He discovered that phenomena, right? When a magnet is moved toward a loop or a coil of wire, an electric current is induced in the wire. Oh, good old Faraday. How did you figure that out? And then the same effect is obtained when the magnetic field is stationary and the loop is rotated within it. Rotated within it. That sure does sound like alternating current, doesn't it? Right? Faraday came up with that? Could have sworn that was like Tesla or something, or Edison. Whatever. I don't know my science history. I don't need to know my science history. So I don't know. Anyway, so your next question is this. Which of the following is not true about generators? It's a device that converts mechanical energy to electrical energy. Generators operate on the principle of thermochemical induction, discovered by Michael Faraday, or all the above is true. And I'll just tell you now, one of those things up there I made up. I just totally made it up. Oh, dang it, I just told you it wasn't D. Dang it. Should I tell you more stories about my crimes or something? I mean, my crime scenes, not my crimes. I hear yawning. So I hear yawning. So that's what I was asking. Ah, generators. 18 people so far. 19 people. You need to get it to 22 at least. I'm so proud. I'm so proud. Almost everybody got this one right. I definitely made up this term here. There's no such thing as thermochemical induction. Totally made that up. Not real, right? So good job on that. Good job on the B right there. The big B for magnetic field, not little b, right? Not little b. Okay, I'm gonna hurt myself with this. It's gonna like poke my eye out or something. Okay, so let's talk about electromagnetic induction. See, in that question, I turned electromagnetic induction to thermochemical induction. I mean, that was a pretty easy way to do it, right? A current is induced in the circuit as a not a magnetic, but a magnet is moved towards and into a coil, right? So here's a meter, right? Detecting current, right? It's detecting current. What is the unit for current? Anybody remember? Yes. Well, I thought it was ampere. No, it's not ampere. You're right, it is coulombs. Whatever. Look that up later. So if you put the magnet inside and out of this coil of wires here, right, you get a current, right? And if you keep on moving in and out, you get this current here. It's pretty neat, right? You should try it at home. Like wrap a coil wire around and attach it to a voltmeter, right? Most people have voltmeters at home. And get a magnet and just go in and out and see if you can make a current, right? I mean, you get tired of it after a while, but it's kind of cool. Kind of cool while it's happening, right? All right, so this is called the AC generator, like I was talking about before. The what is it? Oh yeah, alternating current. The alternating current generator, right? So here I have an amp meter or a multimeter or a voltmeter or whatever you want to call it, right? Um, and so it's connected to this. It's connected to the brushes here, right? The slip ring brushes right here. And then we have a person here, right? We have a person here, and they're rotating this thing here, right? This coil, right, around inside of a magnetic field. And when they do that, we get a current. We get some electricity, right? We get some electricity. So literally, I had a little gerbil at home once. It died. Actually, its mom ate it, but that's a different story. But that little gerbil, he was crazy, right? And on the wheel, like when he was on a wheel, he was like this running all the time, right? And we used to connect that wheel to a thing and just power a tiny little thing with it, a little light bulb or something with it. That's really cool, right? And he was very happy about making light until his mom ate him. So it was sad. It was really sad. Did you know that? Did you know gerbils are cannibalistic? I did not know that. Are you serious? You're killing me. Lion King is like my favorite movie ever. Anyway, transformers serve to step up or step down a voltage of electric transmissions. These transformers consist of two insulated coils of wire wrapped around an iron core. The iron core serves as a concentrated magnetic field when there is a current in the input coil. And I'll show you a picture of it in a minute, don't worry. The magnetic field is resulting from a primary coil that goes through the secondary coil and induces a voltage and a current, right? I don't think you need to know that much about that. I want you to know what that means in real life, though, and I'll show you that in a minute, okay? I'll show you what that means in a minute. So here's your next question. What kind of generator is indicative of a loop that is rotated in a magnetic field, right? Oh my God, this just reminded me of something. So when I took a class called CVA, right, that stands for Comparative Vertebrate Anatomy, the professor, his name was Monty Tees, and he was the weirdest person I ever met in my life, right? And he would run out of things to use to point out things that he was teaching, and so he had this stuff like meerkat, like he got from Africa. It was like a stuffed meerkat, right? And it was like this long, right? And its tail was pointed out that way, and its arms were pointed out that way. And I mean, it was like a stuffed meerkat that was like flat out, right? And he used to use that thing to teach, like he used that as a pointer, like a dead meerkat, right, to teach. And so he also had this very thick beard, right? And it would get very itchy sometimes. And so he would use the meerkat and scratch his beard with the meerkat's talons. It was really weird. Really weird guy, that Monty Thies. Really weird guy. Anyway, I'm just going to tell you the answer to this one is AC, alternating current. Okay? It's alternating current. Okay? I hope you guys got that right. So, this is the step up transformer, right? This is the same kind of transformer that you see that's outside your house, right? And then the thunderstorm comes and you hear this big boom and then the power goes out, right? That's what this is, okay? Happens in my neighborhood all the time because we live in a new neighborhood. So they're right now like trying to put in all the transformers and everybody's drawing so much electricity. So the slightest thunderstorm will like knock out your power for a good, 4 or 5 hours, right? Or during a winter storm for a week. Great stuff, right? So since the secondary coil has more windings, the induced AC voltage is greater, right? So what this is saying is that when you have that coil of wire, right, that's moving inside the alternating current, the more coil of wire you have, the more current you get, right? The more electricity you get. Does that make sense? Right? And so what you can do, just like it's called a step up transformer, is that you can use it to make more voltage, right? You only have a certain amount of voltage coming in to begin with, right? So you input electricity through this primary coil here, right? And it's got a certain amount of current, a certain amount of voltage, right? But then it passes through the secondary coil, right? It passes through and goes to the secondary coil, and the secondary coil has a whole bunch more uh, coil around it, right? A lot more wires winding around, right? And so when that happens, that actually increases the amount of power you can get. It's kind of neat, right? Kind of neat. Science is cool, right? Why do we need to step up voltage? Right? The main reason is to reduce the amount of current that goes through the power lines, right? As the current is reduced, the amount of resistance is also reduced, right? So that makes sense. Say you live at a house, right? And your power plant is like 100 miles away, right? If you have too much power going, then you have so much resistance that power will never get to your house. So they make it low power, so there's less resistance, so the power actually gets to your house, right? But once it gets to your neighborhood, it goes through the transformer, bumps the power back up again, and then you have 120 volts for you to be able to get electricity to power your house, right? That's why these power lines go for so far, and that's why you have to have transformers. Does that make sense? Right? So, uh, if the amount of resistance is reduced, uh, the amount of heat That is that sentence finished? If the amount of resistance is reduced, the amount of heat is. I don't know why that's not there. It's also reduced. That's so weird. For example, if a voltage is stepped up by a factor of 2, the resulting I2R loses would be reduced by a factor of 4, fourfold, right? You don't need to know those numbers, but you just need to know the idea behind it. Okay. So here's here's an equation that I don't really care about that much, but just so I'm like, doing my due diligence and showing it to you, and you can say, Dr. No showed me that equation. He might not test me on it, but he showed it to me, right? uh, V2 equals N1 over N1, N2 over N1 times V1. So the primary voltage, the secondary voltage, the number of windings, and then the number of windings of the secondary coil. So you can actually figure out how much more voltage or how much less voltage you'll get based on the number of windings in the coil. It's kind of cool. So here's the kind of question that someone might ask you, not me, but someone might ask you to solve. If a transformer has 500 windings on its primary coil and then 25 windings on its secondary coil, if the primary voltage is 4,400 volts, what's the secondary voltage, right? So literally you just plug everything in. The 500 goes into N1, the 25 goes into N2, right? And then the first voltage right there is 4,000, right? And so you figure all that out, multiply and divide, and you end up going down, stepping it down to 220 volts, right? 220 volts, which also makes sense too, because understand that when you get a transformer in your neighborhood, right, that electricity has to power the entire neighborhood, right? And I guess some neighborhoods have more than one transformer, but there's a lot of electricity coming from the power line, right, into that transformer, and so he's got to step it down so that each house gets either 120 volts or 240 volts, depending on what you're powering. Like an air fryer, you know, things like that. So this is the picture I really wanted to show you right here. Okay, this is the picture I really wanted to show you. And you might get asked questions about this, right, by me, not by somebody else, but by me, right? Electrical transmission system. Okay, here's the power generating plant, right? Here's the power generating plant. And in the power generating plant, we're making like 24,000 volts, right? So that could be like the nuclear power plant, like the one that Homer Simpson works out in Springfield, right? Or it could be a dam, all kinds of stuff. Could be this electrical generating plant. And it's pushing out 24,000 volts, okay? It goes into a step-up transformer, right? Right, to get to these antennas right here, not antennas, these transmission wires, power lines up here, right? And then after that, it actually gets stepped down to 100,000 volts, right? And it gets stepped down again when it gets to the distribution substation to 20,000 volts, right? And the reason why it's going down, is because you want to reduce resistance while you're going over a very long distance. Does that make sense, right? It takes too much work to push a lot of electricity through these power lines. And it just keeps on going down, and now you have your utility pole at your house, right? And there's also a step down or step up slash step down transformer right there, right? That's that big thing right there, that that cylinder, 2 cylinders, right? And that's what brings electricity to your house at 240 volts. Is that crazy? It's good stuff, right? Good stuff. You definitely don't want to take power straight from the distribution station without going to your electricity poles, your utility poles transformer, because if you didn't, it'd come straight to your house as 20,000 volts, and then everything in your house would explode, right? Your iPhone, your TV, your your Switch, your PS5, your computer, your air fryer, everything you could think of would explode, right? So this is how it goes, right? Generating plant, 24,000 to long distance transmission, right? Is at the highest right there is 230,000 volts. And then it goes down to 100,000 volts at the area substation. Then it goes down to 20,000 volts at the distribution substation. After that, it gets to your utility pole, and that utility pole is what transfers it to 240 volts for you to use in your house. And then there's also a tiny little transformer inside your house too that makes it 120 volts for the your normal appliances. Make sense? It's good stuff. So, what voltage of electrical energy finally makes it to your house? Such a good time. Such a good time. Such a good time. Has everybody done their answer? Let's see how people have answered this question. And this is not a trick question. And it is asked correctly. At least I think it's asked correctly. Ah, there we are. No, that's not it. Ah, there it is. 22 people have responded, and the vast majority of you got it correct, right? The answer is, in fact, A, right? It is 240 volts, okay? And you do get power at 120 volts in your house too, but it doesn't come to your house at 120. It comes to your house at 240. Otherwise, you wouldn't be able to actually power your clothes dryer, right, or your water heater, or your what else does it use? Your oven, right? Your oven. All right. That actually ends today's lecture. There's some, equations there. It's not like you need them, but there's some equations there. Don't tell anyone I didn't give them to you because they're there, right? And that ends today's lecture.